welcome to the HPL seminar. Thank you for joining us today. Today, it is my pleasure to introduce Maahika Mehta, who is a first-year biomedical engineering master's student with Dr. Sayebaya in the Healthy City Lab. Maahika recently graduated with a Bachelor of Science honors in biomechanics, where she conducted research with Dr. Gait on muscle adaptations to power training in youth with cerebral palsy and the female gut-bone interaction. Driven by a passion for data-driven biomechanics and product innovation, she has already spent time working with Garmin Canada, sport product testing, and biomechanics. Now in her master's, Maahika is excited to continue exploring sensor-driven approaches for gait and frailty monitoring in collaboration with Orpix Medical Technologies. When I asked her about a fun fact about herself, she said that her name means earth in Sanskrit, which is fitting connection given her love for running, biking, climbing, and seizing every opportunity to spend time in the mountains. Today, she will be sharing her research that she conducted in the NIC group over the summer on exploring wearable sensory insoles for gait assessment. Thank you, Mehta.
Thanks so much, Ashna. All right, let's dive right into it. So global life expectancy rates are estimated to steadily increase over the next several decades. And with an aging population, we unfortunately also see increases in chronic disease rates like diabetes, heart disease, stroke, and cancer. And these chronic diseases continue to be the leading cause of morbidity and mortality worldwide. The burden this puts on our healthcare systems is quite tremendous, as by 2030, the estimated cost is to reach around 47 trillion. And so several of these syndromes also come with other repercussions like disturbances in gait patterns, increased fall risk, and frailty. However, these changes in gait patterns may also be useful for early diagnosis and prevention. And so gait assessments have been proven to be strong tools for accurate identification and monitoring of gait patterns. But despite being present for more than 3 decades, these gait assessments remain limited to lab-based testing associated with high cost, limited accessibility, and limited transferability into clinical real-world settings. And as a result of this, qualitative screening measures and tests for clinicians are prevalent, even though these subjective tests may have less efficacy than quantitative gait measures. Compared to traditional lab-based testing, wearables provide ease of use and objectivity in quantifying gait and mobility, either through traditional in-clinic observational assessments with visual and remotely administered home-based assessments. They also provide the ability for an individual to record their daily living data and get clinical insights right at their fingertips. There are already some established gait monitoring technologies. For example, iPhones have built-in features to identify when a user is walking over ground in continuous segment, and then outputs these metrics. And so this is obviously what the phone in your pocket. The Apple Watch can also provide additional mobility metrics. However, some challenges that come with this are certain estimations or assumptions because of the location of the device or the sensor. And so there is opportunity for improving precision, depth of biomechanical insight, and relevance as to how these values compare to other traditional normative reference thresholds. Foot sensory insoles are a relatively novel method for gait assessments, and they're useful because they allow easy accessibility in settings outside of traditional labs and can provide measures of foot kinetics and kinematics. Orpix is a company that produces these insoles as personalized health solutions for individuals with diabetes. And so coming to this project, I wasn't aware of that connection. But for example, for those who have diabetes type 1 or 2, There are at a high risk of developing something that's known as diabetic peripheral neuropathy. And so this is a major complication that impacts the peripheral nervous system, and thus on sensory and motor function, increasing gait abnormalities, and then leading to more risks of falls, for example. So these insoles are comprised of pressure sensors, temperature arrays, and inertial measurement units, also known as IMUs. These pressure sensors and IMUs are the most relevant kind of data inputs for our discussion today. The aims of my summer project were to use the Orpix insole data to calculate gait metrics for a small sample of healthy subjects and individuals with diabetes to generate an individualized multitask gait metrics report. In the data set, there were individuals with diabetes and healthy that performed 3 main tasks of walking, standing, and stairs with a variety of different conditions, as you can see on the screen. And for the development of the algorithms for this project, I ended up focusing on 4 subjects with diabetes and 2 to 3 healthy individuals to develop reference records. And so future directions for this work would obviously be implementing it across the larger Orpix dataset. So now let's walk through the metrics themselves. After reviewing some of the literature in this area, I focused on 4 that would give insights surrounding fall risk and balance. So first, for the walking data, toe clearance. This is the minimum vertical displacement during roughly middle of swing phase of walking. And so this is where we'd see the highest horizontal velocity and thus tripping risk. For the stairs task, I looked at stride time asymmetry. And so this was determined by calculating the stride time. So time between consecutive heel strikes. Subject wore insoles both on the left and right feet. And so you would average the stride times for a certain trial and then calculate a symmetry index to compare both limbs. And so in general, more asymmetry between the limbs suggests greater atypical gait patterns. For the standing tasks, this was a double-legged kind of balance task with both eyes open and eyes closed. And there were 2 metrics to look at. Firstly, in general, the center of pressure position data from the insoles was used. And so firstly, we have the path velocity, looking at the rate of an individual deviation from stable central position. And then the peak path velocity is looking at the maximum values for the trials. So greater peak velocities indicate more movements and challenges in regulation. Lastly, for the standing task, it was the postural sway area, also known as the 95% confidence ellipse area. So simply greater area would mean that an individual is having more difficulty with postural control and is moving around more on the spot. So you can see that there's a blue overlay on top of the center position data that we can see for this subject here. So the goal was to combine these metrics for the various gait conditions in a report output as presented here to give a holistic measure of an individual's gait profile or blueprint. So now we'll walk through the steps that kind of led to the development of this framework. In terms of the first step, which was data processing, to get to a point where we can extract these metrics, there was a number of calibration, conversion, and filtering steps. The insoles provide raw plantar pressure and IMU data. So then we had to go through these steps to get us to the gait event detection. So this was kind of a sub-investigation for me this summer, being able to figure out when an individual is in the swing or stance phase of walking, for example. And so in general, as most of you are aware, force or plantar pressure data is the gold standard for gait event detection. However, for a device like a sensory insole, these pressure sensors are prone to degradation over time. And so in theory, we can use the IMU, gyroscope, and accelerometer to get these gait events, which is thought to be more robust and consistent. And we can see here that in each signal trace, there are certain key characteristics identified from the literature that correspond to heel strike and toe off. And so I kind of used that as a background to then look at and parse through our data. And there was some observations that I saw. So firstly, the signal features outlined in the literature didn't align exactly with the force-based gait events. So the IMU would overestimate foot contact and underestimate foot off. And then when I looked to comparing different subjects, I realized that the signal features also differed here. And so foot contact for this subject would similarly, yes, be overestimated by the IMU, but the foot off peaks actually aligned pretty well for all three signals. And so in general, there was subject to subject variability, which produced some challenges for this objective. Because of these inconsistencies, I arrived at the conclusion that although IMU gait event detection is feasible and it is valuable, it did require some more complex algorithm development. And so I decided to go with the plantar pressure based force event detection for the scope of the project this summer. And then obviously we can use that as a base for future development. So now, once gait event detection is done, we're ready to compute the gait metrics. And I'd like to walk through two examples of the metrics that we use the COP and the IMU data for. So first toe clearance and then postural sway area. For toe clearance, to re-emphasize, the time point in the gait cycle where this is most relevant is roughly in the middle of swing phase of walking. And so if we imagine the leg is sort of like a pendulum here, it's closest to the ground in terms of vertical position, and it has the highest forward or horizontal velocity. And again, that means higher tripping risk. So we start off by extracting the IMU data from the walking trials. We get the raw signals, and then these trials had some extraneous data for various system alignment. And so that wasn't useful for our computation. And so there was a step segmentation manual process that was done. And then after going through some filtering steps, we're now ready to do the gait event detection, which essentially with the plantar pressure data and that method returns instances of heel strike and toe off. Applying those indices to our signal of interest for toe clearance comes from the 3D linear acceleration data. And to go from acceleration to displacement, obviously we do a double integration. And so for IMUs, this introduces something called signal drift, where over time minute errors add up and the signal deviates more from the accurate measurement. And so we needed to do some correction steps to essentially get us to the corrected vertical displacement of the foot at the location of the IMU. So now we can use this signal to assess toe clearance moving forward. The IMU in the Orpix insole is in the middle of the foot. And so here we get the trajectory of the midfoot, as you can see outlined by the red curve. But we want toe clearance. And so there was a need to do a linear projection using simple trigonometry to get from the middle to the toe position. And so this was also done using some sensor size configurations provided by the Orpix team. And so after projection, we get this blue, nice toe trajectory, but you may be wondering why there's some negative values during the early kind of swing phase. And that's again because of the projection. So the toe is always in relation to the middle of the foot. So when the foot is in severe downward motion or orientation, there was a bit of an overestimation of the toe position. And so we have these negative values. To combat this, we had to make the assumption that right at foot off, the toe is at ground zero. And so this became kind of like an offset to shift everything up and a way to correct for the position. So we have one piece of the puzzle, and the other is finding the actual point of minimum toe clearance during swing, which we know the foot has the greatest horizontal velocity. So I was able to look at the velocity graphs, find those maximums, and then map that back to the position data, which is depicted here by the green X. So all that to say that the delta between the green and the orange markers is actually our toe clearance for the different walking conditions, and we were able to apply that for the different subjects. So that was one metric. And then pivoting over to the standing tasks, I used the plantar pressure data for metric calculation. And in this figure, we can see that on the y-axis is the anterior posterior center of position, and then on the X is the medial lateral. The individual here, we can see starts a little bit more posteriorly, indicated by the red, and then they move forward by the end of the 20 seconds. And everything is overlaid with a red 95% confidence ellipse area. And so greater deviation on these plots means more movement, indicating less stability. And those were the kind of insights we were able to pull from this specific metric. So after calculating the metrics, the 4 metrics, I processed the data for individuals with diabetes and healthy subjects to kind of compare the values. So we'll break down the findings by metric, and to note that these results here are highlighting trends, but not statistical differences between groups. So first, for the walking toe clearance, I found that as hypothesized, subjects with diabetes trended towards lower toe clearance values, indicating that they had more challenges lifting their foot from the ground during swing phase. And it also seemed that the walking conditions that led to that behavior seemed to be dependent on the individual. Next, for the stairs, stride time asymmetry. The symmetry index here is on the y-axis in percent. And as expected, greater asymmetry between limbs was seen in individuals with diabetes, but the effects of stair gait type, so whether we saw ascent or descent conditions perform worse, those were highly variable and individualized. For the standing metrics, and firstly for peak path velocity, on the figures here, we're comparing the path between an individual with diabetes on the left and a healthy subject on the right. And in both directions, we can see that peak velocity was greater in individuals with diabetes. And that's suggested by the amount of deviation from the center for the subject on the left. So in general, there was greater magnitudes of sway. According to the literature, anterior posterior peak path velocity is the most sensitive measure for postural control assessment. And so I looked at that specific direction for the larger cross-subject comparison. And again, we saw greater magnitudes of peak velocity in individuals with diabetes. Lastly, for the postural sway area, we can see the center of pressure path here overlaid with the 95% confidence ellipse. And individuals with diabetes had greater ellipse areas, which again meant that they had a harder time regulating their standing posture. However, that came with a caveat, because even in healthy subjects in typical gait, when I looked at the different sessions, so these sessions were taken a week and a half apart, there was a lot of variability for the same condition on the same foot. So that raised the question of whether these differences were clinically meaningful or just subject to this specific metric having a lot of fluctuation. And so that brings us to the final objective, which is putting these pieces together in the final individualized gait report. This is an example of the current iteration for the automated gait assessment. It intakes the comprehensive metric data and outputs this visual report. In terms of the ranges that we see here, they were developed from the literature values when available. So for toe clearance, there was some literature that I could pull from. And for instance, for stride time asymmetry and some of the standing tasks, I used calculated values from the small pool of healthy subjects as guidelines to set these bounds. And so the green areas are typical healthy ranges. The yellow is moving slightly towards risk zones. And then the red is high risk, potentially danger zones. And so this being a primary exploration, we take into consideration that there's obviously limitations to this specific approach. There are several ways to go about this referencing and finding these thresholds, but this was kind of a starting point for future developments. So what does this data look like when we compare different subjects? Here we have two individuals with diabetes and a healthy individual in the middle. A couple observations to point out. Firstly, some metrics were a little easier to distinguish typical versus atypical gait patterns. And so, for example, for the toe clearance or the stride time asymmetry. But for other metrics like the standing metrics, even healthy participants presented in the yellow or red ranges. So this reemphasizes firstly the importance of individualized reports, but then also presents opportunities in terms of thresholding. So either we take a larger set of age-matched healthy participants and then look at that normative data, or considering that there was significant variability, even in healthy subjects, maybe within subject comparisons are more appropriate. So comparing an individual's baseline gait assessment and then getting them to do that assessment at multiple time points to monitor trends over time. So those were a couple ways that we could think of how to take this project further in the future. And so overall, this work revealed the possibility for longitudinal gait monitoring, observing whether these trends remain the same or they increase or decrease over time in clinical groups. And taken together, the Orpix wearable technology has strong potential to provide insights for fall risk and balance, and that valuable metrics can be derived after fine-tuning for task and variability for future on-demand assessment and report developments. And so I'd like to thank the members of the NIG group and the Orpix team for their continued mentorship and guidance throughout this project, and to all of you for your time and attention. Thank you.
Floor is open for questions. Who would like to start us off? Yeah, some questions. Sorry.
Great. I think like, thank you that was a really nice presentation. Looks like a lot of work for data processing, like for a couple of people to end up where you ended up. I guess my question is, did you look at precision and measurement error in the first place? Because there's a lot of like fiddling with filtering and such to ensure that like you measure yourself twice in a row that you're gonna get the same values for the centers.
So this data came from a larger project that was done last summer from the team. And so in that, they did a lot of like validity and comparison metrics. That wasn't specifically the scope of this project, so I didn't focus on that as much. But they did go through some of those tests, and after kind of fine tuning, I was able to apply that for this project. Yeah.
Colin, did you have a question?
Yeah. Hey, I'm curious about the relationship that neuropathy has with some of these measures. So did you were you able to like quantify the degree or the extent of neuropathy that they had? Is there a method for that, or how does that go?
Yeah, it's challenging to quantify for sure, but I think that I guess this is the first step to be able to move towards that. I wasn't able to kind of get like an index or like a risk rating for someone that potentially could develop peripheral neuropathy, but for example, we obviously see a lot of like gait abnormalities, and these points of fall risk and balance are very relevant to someone who would be at risk for peripheral neuropathy. And so I think this would be kind of the first step. And then the next step would be, can we kind of fine tune these metrics, get those thresholds a little bit better, and then maybe use some advanced techniques to then get those indices. So not for this project, but I think that would be an interesting kind of next step.
I have a question about the stride time asymmetry that they brought. So if you're just walking over level ground at a constant speed, how can stride time be different between the two legs? Because, I mean, you have maybe one shorter step, one longer step, but a shorter and a longer step is the same as a longer and shorter step, so. Wow, so I guess it has something to do with what exactly you did with your stride time measurements, whether you took averages or directional, or also how many steps they actually took up the stairs. That would be very interesting to know.
So, I can go over kind of what the index was. And so you're right that for stride time, over ground, it would be a little bit different than, I guess, my use case, which was over stairs. And the reason why the stairs kind of data or the stairs task was looked at is because clinically, in older adults, it's known as to be a little bit more challenging of a task. And so for someone who has frailty, maybe they have more difficulty kind of walking upstairs or produces more challenges. So the first part is that's, I guess, why we looked at stride time asymmetry for stairs. And then specifically for the symmetry index, it's more so trying to figure out if there were, I guess, imbalances for the 4 to 5 kind of steps that they took going up or down the stairs. And so it was kind of a limited, shorter data set. I agree that if we had a longer kind of trial time, that would definitely add more value. But for the data that I had, it was shorter, and so I kind of used within the parameters that I can.
Yeah, I would actually argue the other way around and say it's super that you have a short trial, because then those first and last steps that you do, they can actually contribute something to the asymmetry. Because if you have like a flight of 20 stairs, this is sort of like steady state movement. So you wouldn't expect any differences in stride times between the right way. So I think it might be worth looking at the initial step and the last step up the stairs and see how this helps you maybe with making this stride time asymmetry a better measure.
Absolutely, thank you.
Okay, I have a question. So I noticed that in your results where you had the toe clearance results for healthy versus diabetic populations. If I'm remembering correctly, yeah, so the result where you concluded that the diabetics have lower toe clearance compared to the healthy adults seems to be driven by the fast or the cognitive task to me. And I'm wondering, was there a difference, a substantial difference in the age of the healthy versus diabetic populations? Because from those red and green bars, it seems to me like, is the age playing into the role, or is that actually the diabetes?
Yeah, no, for sure. The healthy controls were not age matched, so they were around 20 to 30-year-olds, and so comparing them to a significantly older population would again produce confounding kind of results. But I guess for the data set that we were working with, and for this, I guess, investigation, that was a limitation that was present. And so I think moving forward, definitely what I mentioned about getting a larger sample size of normal healthy age matched participants would be of value for then comparison for metrics.
Awesome.
Yeah, if I'm not wrong, when you say toe clearance, you mean you found it from IMU, right, on the feet?
Correct.
Okay. So you don't have the location, position of the toe in real life, right? In reality, do you measure the toe position?
We estimated the toe position using the IMU vertical position, which was in the midfoot. And so we projected that from midfoot to toe.
How do you do that projection again?
So I can give an example. We have the blue line here in the middle is the position of the IMU. And then this was a simple linear displacement to then get the Y and the Z indices of the toe. So again, this is a very basic rudimentary method for toe position calculation.
But did you measure individually what is parameters for everyone?
So we calculated individually for everyone, yes. But not validated against any other kind of method. I'm not sure if that's what your question
It's
is.
just called, that's what you are looking at is the patient population, not diabetes.
Correct.
Okay, if you only look at IMU position, but you have a formation here, there are maybe infinitely many possibilities that IMU vertical position is gonna be same, but toe clearance in real life will be different, such as this is the foot, IMU is over here. Someone doesn't have, say, drop foot or something, and they cannot plant flex or dorsiflex, right?
Yeah.
So someone is like this, and someone is like this. So do you see kinetics are different? So toe position to ground is different, but you are calling it toe clearance.
Absolutely. I think,
Okay, you know that, you know?
yeah, no, I agree, and I think that might be, I guess, the way that we've defined this metric, but you bring up a good point, in terms of clinical populations. For
I
sure.
think Brent has a comment.
But are you projecting the vector in the direction of the toe?
Yes,
Would that change what you're saying about this?
If you measure from the IMU to toe and also it depends on what shoes are they are wearing and such, shoe thickness and such, you know, in real life, you don't know the location of the toe really. Toe clearance, the trip happens like this, right?
But how big is that difference? Because if you have the orientation of the IMU and you know your toe is in this location and the
Do you really
IMU,
know with respect to IMU, the toe location is
I
the
think you can measure that, no?
Also, the thing is, kinematics are different with patients, right? Ankle kinematics. So if we assume everyone walks very similarly, like healthy people, that will be more valid, but ankle kinematics are different between patients,
So you
right?
don't need to assume that because you can measure the displacement
From IMU
from the
to
IMU and you have the orientation of the IMU, so you can project from the IMU relative to the IMU reference frame to the toe.
I think
But
that's
there are-
the
but-
point that Brent and Tilo are making, I think was also clear from Mahika's graph of the projection where you did see that the toe is relatively, inferior or whatever, below the location of the
But
mid
you
foot
don't,
ankle,
you
right?
still don't know the kinematics while the motion. Okay, I have the ankle and I have the toes and they can move and we don't know how they move,
I don't
right?
care about the ankle in my IMU.
Okay, do we have a
Okay,
question moving in?
That's what I'm saying.
I don't know, so it's not like a sort of fixed distance from the IMU to the toe.
Yeah, but okay, how
much
about you move?
Okay, like that.
Okay, next question.
That's not something.
I love this.
I think that's a great discussion over years after saying. But yes,
Okay, back to the IU. Can you talk more about the method of displaying the results for the individual? So what I was confused about is on some measurements, you have this red zone, this yellow zone and the green zone. Some yield a green and a red. And then the top one, I'm seeing like a red and a yellow and a green, then a yellow.
Mhm.
So can you just maybe just explain that a little bit more?
yeah, absolutely. So we'll start off with the toe clearance. The reason why it starts off with red is assuming that someone has extremely low clearance or position from above the ground. That's bad, because that would obviously mean that you're gonna trip over your toe. And then the reason why, like, we increase it a little bit, and so that becomes that yellow zone. It slightly risk, maybe you're lifting your toe a little bit higher, but potentially maybe you're moving towards having greater tripping risk. And that middle zone is the good, healthy, according to literature, it's roughly 2 to 8 centimeters, if I'm recalling correctly. And then if someone's lifting their foot too much, maybe that's an indication of they have a fear of falling, or they're a fear of kind of tripping, and so it's a increased kind of vertical position. And so that's why it kind of changes from red, yellow, green to back to yellow.
So when you say literature based, I mean, there's literature that kind of says it's bad if it's the toe clearance is between 0 and X centimeters, and then it's risky if it's between X and, yeah.
Well, no, that's where, it would be great if it did, because that would make my life so much easier. But, some studies that have, I guess, just measured toe clearance using motion capture in healthy individuals and then clinical populations and compared the values. So that's what the data is present, and so I use that and then extrapolate from that.
Okay.
Yeah.
And this is, I don't know if this is something that you thought about, but it's something I think about a little bit, like real world scenarios, very unpredictable. Toe clearance, there's gonna be somebody that's walking their dog that needs to like lift their leg and step over the leash. And it's gonna get into like this risky zone, right? It only happens once. So if you're gonna take something like this and this is different, because this is like, you're just kind of giving somebody a holistic view of where they land. But if you were gonna develop a system to like beep or call the police or something, I don't know. What would you do? Like, do you have to collect a lot of toe clearance data to get a sense of if this person is at risk, or do you think one is enough, or?
Yeah, a lot of data would be ideal because of, again, individual gait pattern variability. For someone who is healthy but still just has a really weird way to walk, that would mean that their, I guess, toe clearance would be different than someone else for sure. So firstly, yes, a lot of kind of similar assessments over a long period of time would be valuable. And then the other thing is, it'd be really cool to integrate like activity classification into, and more context into then some of these walking tests. So in like a real world situation, if someone it says or puts kind of the factor in that they are going for a walk with their dog, maybe that changes the threshold or the ranges a little bit because it adds an increased risk component. And so I think either automated activity classification, or the simple way is like, it's a first step into the program and then it kind of goes from there.
I actually love this. So,
Yeah.
are you familiar? Has somebody done the research? People wear watches, activity monitors, all these kinds of things. Can you predict with some reasonable accuracy whether or not somebody's walking alone, or whether they're walking with a dog, or whether they're walking with a friend? Do you know?
I don't know about the different walking conditions, but I do know there is work like comparing walking versus running versus I guess those are a little bit more easier because accelerometers, obviously running, you're gonna see greater. But I'd love to look into that and see if we're there yet. I doubt it though. I think we're moving towards that direction, but.
Stop every once in a while for the dog to do its business. Maybe that's a
I think
event detection.
the Apple or like Garmin watches and stuff, if I'm not wrong, they do can detect like if you're outdoor walking or like doing some sort of hike or something versus like looking at walls. But I don't know if they could tell if I'm with my dog or my friend. Yeah, try to do the same thing.
I probably it's not a question about unused. So if you're going down that route and you're collecting masses of data, do you think you find more clues in what the average of a person under certain conditions, or maybe the variability, or what do you think is actually the most interesting out of what you do?
It would be nice to see trends over time. I'm not sure if that's what you mean by averages. But I guess if someone has some kind of surgery, lower limb surgery, for example, and then we obviously have an established baseline like pre-surgery, and then I guess in terms of like rehabilitation or something like that, from such an event, or even like a fall, someone who had a fall. And then seeing like time back to returning to their initial healthy state, or I guess specifically in like a clinical setting, how can like clinician use this to help rehabilitation strategies? So I think that would be a really interesting application for this work.
Okay, two hands, Matt, Lee, and then, or the other person. Okay, Matt and Lee.
So are there any other mechanical variables that you could pull from the IMU that would be maybe a better proxy for the condition? It seems like it's kind of hard to figure out, where that toe clearance is, but like, what about how much push off you have, or rotation, or
I was even just thinking like, if you were using this in the real world, like, do you sort of have event detection where you catch your toe and you pick up the number of times that people catch their toes? Like, I was just thinking about the other day, I just got these new shoes. They're a little bit wider, and I've noticed I caught my toes a couple of times just because they're different than what I normally wear.
Yeah.
But I would imagine somebody like this might have more instances like that.
Yep.
Where do you go with that?
No, absolutely. There are so many different metrics and variables, like temporally, spatially, spatiotemporally, that you can get from IMUs, which is, I guess, the benefit of such a small device, and you can go in so many different directions. So yes, there's a lot of things that we can look into. The limitation, I guess, of this is I looked at 4, but there's literature kind of supporting the fact that maybe if we look at like propulsion phase, and the time in propulsion phase or different phases of the gait cycle even, that could maybe be an indication of different clinical conditions specifically. So I think I don't have a direct answer as to this metric equals this condition, but I think that would be like the next step into some definitely things to look into.
Do you have a top 3 that you might like to look at?
I really do think the toe clearance one is valuable, so
Okay, so
that
that's
might
number
be
1.
controversial. Yeah, and then I also think that the postural sway area in terms of like balance, and the amount of like, I guess, how much deviation there is in direction, I think that's valuable as well, because if I go back to kind of this, these maps, the individual on the very right with Parkinson, we can see a very large kind of ellipse that around it. So I think those two, and then I guess the third one, I think it would be cool to look at like propulsion, or different acceleration phases and maybe like time, during those phases. And so I think, yeah, that would be one that I haven't looked into yet, but it would be something cool to investigate.
Yeah, no, my question was just kind of like Matt, if you got these 4 outcomes, but like 9 within all of them. Do you need all 9? Like if the goal is fall risk, if I see myself like green for 8 categories, I guess which I'm great, but is it really the systemic that's more predictive of my fall risk?
Yeah, so these different conditions, I guess, were there because they add some level of difficulty or challenge. I thought that maybe like descent, we would see those distinguished kind of patterns of like, okay, someone is having more difficulty going up versus going down, but we didn't see that. So I don't know if we do need all of these different conditions, but I do think adding in conditions where there's increased challenge is good, because then we can really test when someone's thinking or cognitively challenged, cognitively a demanding task, what are the differences that we can see? So maybe not all 9 conditions, but I do think some kind of permutation combination would be good.
And I guess what's like is the next step to bring in some frequent callers and measure them. I mean, you've got diabetic, non-diabetic, but again, don't know how severe the conditions are. So
Yeah.
would that be more insight?
Yeah, that would be great. It would also have been so great if we could do like a questionnaire before we even went into this to get more of that data and like demographic data as well. But I think for my master's work, which is focused on frailty, using these sensors, that will be an important consideration to take into account.
Robin?
I was just wondering why you did like those postural sway with eyes open and closed, and do you think you can gain some insight about comparing them together?
So eyes open and closed was done because typically when we close our eyes, we lose kind of spatial awareness. And for individuals with peripheral neuropathy who maybe don't get that peripheral feedback, that becomes a lot more challenging. So that was why eyes open versus eyes closed was done. And then comparing them, yes, comparing them definitely would give you better insight. But I guess a follow-up to your question is like, we're kind of comparing them here. How do you think like it could be done differently?
Same as clinically, there's a ratio or difference, and I'm also looking at your boundaries here, they got the same thresholds for eyes open and closed, but you expect to more if eyes closed, I would expect the boundaries to be also different.
Yes, or I guess the approach that I was looking at is like, for comparing like to like, if we do see eyes closed being worse, then we would see shifts, but I guess I see what you mean is like that ground or that typical with eyes closed, we would maybe everyone is just bad at it, so then we maybe do see threshold shift. To answer that, I would need more data to look into, but no, good point, Sarah, thank you.
I think how I think about that, like if you're bringing people into the lab, you're already taking away so much stimulus and extra environmental factors that might affect how they're moving in real life. And so I think having the same thresholds to me makes sense, because when you have them in the lab and you make them close their eyes, maybe that is replicating a little bit of what they would do in real life, where I'm cooking, where I'm thinking and I'm shopping and I'm not thinking so much about how I'm walking, which I would in a lab. So maybe that helps to replicate some of those tasks. I don't know, but just thought point. Any last questions for Maahika?
Sorry for coming back to the toe clearance.
No.
Integration, and I wonder where you got the integration constants from.
Yeah, so here, let me go back to this slide. So there were times, so instances when we know that the foot is flat, so mid strike, we know that the velocity of the foot is 0, and so those were used to then get those constants and then kind of adjust for the displacement.
So somewhere in mid-stride, you assumed that the vertical velocity was 0 and the displacement was 0.
Yes, correct.
And I was just thinking when you walk, and your transducer is there and you go there. I was kind of thinking it's kind of moving up and down all the time. So I thought getting that instant correct might be difficult, or you find that relatively easy, or
I wasn't involved in this specific piece of the algorithm development, so this was, I guess, something that's done in the literature is known as like the foot flat correction method. So I don't know the intricacies of how this was developed, but this was a kind of a pre-developed method that I applied for this, but I agree that yes, there are obviously some minor kind of changes or increases, decreases of velocity, but I think perhaps it's like compared to the acceleration we'd see when we are at toe off or heel strike, it's less, and so there's a threshold that's used.
so in gait analysis, it's accepted to do that with.
Yes.
And then again, toe clearance, I was thinking about what would I expect? And I was surprised when you had the result that people, the patient with diabetes had a lower toe clearance, because I've seen studies with elderly and they seem to have a very high toe clearance because they don't seem to be safe, and they also have a wider gait because they don't feel so safe. So if I was a diabetic and I wouldn't feel quite as comfortable, I would have expected the toe clearance to be higher, and the more confident I am in my abilities, the lower. So can you explain to me why I might have expected exactly the opposite result?
Yep, good point. And I agree, there was a paper that I referenced earlier by Suda and colleagues that found that, when looking at individuals with diabetes, they actually had higher toe clearance or toe clearance that the differences were negligible. So I think it can go either way of, you either can kind of lift your foot super high from the ground, or for someone who does have drop foot or has a harder time just lifting their foot, we see extremely lower values. So I think it can be in either extremes, and it's those extremes that we want to catch. And clinicians want to be able to see.
So when you look at that angle, right, at the lowest toe clearance, the ankle angle, did you find that was different between your subjects with diabetes and your control subjects?
So
Did they have more of a drop foot, for example? Or?
I didn't actually look at the ankle angle, but I think both you and the gentleman at the back brought up a good point, and I think that would be something valuable to include, but I didn't look at drop foot angle for this study, no.
The other thing I was wondering is, when Then you have the people, standing on the platform and balance test. What do you tell them? What's the command?
In this data collection, and I don't know the exact words, but I believe it was just, like try to stand quietly and as still as possible. So quiet or still stance.
So we're still as possible. That would make sense then. So then you assume if you have better control, the area would be smaller.
Correct.
Because again, I was thinking, if you just said, oh, just stand comfortably here, then if I feel very comfortable about my balance, I could easily see that my swaying and peak velocity might be bigger because, hey, I'm very comfortable. I trust my muscle.
Absolutely.
It's kind of like if I walk along a balance beam, I probably walk very carefully with the variation, whereas gymnasts make somersaults and everything. They can do lots of stuff because they feel very comfortable and they have better balance, so they can, but it's as still as possible. That makes sense. So based on your pilot data and realizing it's pilot data, would you be able to say something to the people that have diabetes with your recommendation that comes out from this study?
The recommendation piece, I think would be the best if a clinician is able to kind of analyze this report. And I think they'd have the best gauge of what recommendation to give. I don't think I'm in the position to do that, but in chatting with some of the clinicians on the Orpix team, they think this would be a great start. But even as we were talking about earlier, like an index or like a score, if we could get to that point, that would be the best, I guess, comprehensive way to then be able to give a recommendation moving forward. So I think this would be a first step, but not immediately ready for me to be able to give a recommendation. But I think from a clinician interpreting this, yeah, they could take this and kind of assess it with their patients.
Very often diabetic patients, I think the primary concern is not so much falling. The primary concern is that they develop ulcers on very, very bad inflammation and ulcers at the bottom of the sole there. Did your patients have any neuropathies that actually they had?
Yes.
Ulcers that potentially might affect how they behave?
Yes, some patients in this data set did have neuropathy, differing levels of severity. And I agree that would impact some of the gait patterns we're seeing. I specifically didn't look at ulcer kind of diagnosis or develop metrics that would help kind of prevent that. But the insole does have kind of temperature arrays, which with ulcers, we would expect to see hot spots over time. And so that is something that the Orpix team is looking at, but I didn't investigate for this project.
So just maybe final question, is that, the speed test essentially that you did, do you think there might have been variables there, parameters there, that might have been equally valuable in assessing the risk of fall, or maybe even more valuable than what you measured or quantified?
Sorry, can you repeat? So other variables?
You measure the toe clearance, the symmetry, time symmetry, the oval, the balance over there. Can you think of other parameters that might have potentially been useful in further evaluating or give more information about fall risk in these patient populations?
Yeah, for sure. I think gait speed is a dead giveaway, like in the literature, it's very kind of known that if someone has a lower kind of speed of walking, that they are firstly maybe at kind of indication of frailty or fall risk. So that would be a giveaway. I chose these metrics to be maybe something that hasn't been investigated as much in the literature as kind of an exploration. But yes, there are many parameters and many different ones that I could have looked at, but I specifically chose these four. But
So you chose them?
yes. I
They were
decided.
not given by
No,
Orpix or?
no.
Okay, good for you.
All right, with that, let's thank Maahika for her talk.